stop you right there. I'm the Baked Potato Animator, and you just watched The Big Bang. No, not the TV show. This is the real deal. The Big Bang converted pure energy into elementary particles, which are the basic building blocks of all matter in this universe. Elementary particles include many things, such as leptons and bosons, but we only need to worry about quarks and electrons. Shortly after the Big Bang, and I mean immediately, like a fraction of a second, up and down quarks formed protons and neutrons, which quickly bonded into hydrogen and helium nuclei, or the core of an atom. These weren't really atoms yet because it was too hot for nuclei to catch electrons. But wait 380,000 years later in the recombination epoch, and it is cool enough for electrons to be caught into real atoms. If we want to learn the history of every element, we must first understand atoms. Elements are classifications of atoms. What makes each element different are the amount of protons in their nuclei, or core. The atomic number of an element is how many protons are in the nucleus. The atomic mass of an atom is how many protons and neutrons are in the core combined. If I say helium-4, the 4 is the atomic mass. Finally, we have isotopes of atoms. Some elements may have different isotopes because they have a different number of neutrons in their nucleus. Carbon-12 and carbon-14 both have the same amount of protons, but different amounts of neutrons. That was your crash course on atoms, so now let's get back to it. After the recombination epoch, nothing really happened for the next 200 million years. This complete absence of literally anything was called the Dark Ages. But wait, is that hydrogen and helium gas? It's clumping up. The gravity of the gas is attracting more gas and more and more. The gravity is condensing the gas. It's getting denser and hotter and denser and hotter and denser and hotter. And wait, it's starting to burn. It's a star! Now, stars are the star of the show because they do one simple thing: nuclear fusion. Nuclear fusion is when two elements fuse to make a heavier one. Nuclear fusion only happens under extreme conditions like extreme heat and pressure. Now you can see why stars are so important. This releases energy and fights against gravity, eventually landing in equilibrium. Stars start off fusing hydrogen. So what's hydrogen plus hydrogen? Helium! This goes on for the star's lifetime until there is a lot of helium in its core. So much helium that it ignites. Helium burning. Hydrogen gets pushed out from the core to the hydrogen burning shell, leaving helium burning in the core. The star is now in its red giant phase and is absolutely huge. So, what's helium plus helium? Beryllium! But wait, beryllium-8 is super unstable. Like, it decays in 8.19 times 10 to the negative 17 seconds. That's 0.00000000000000819 seconds. But when there's a lot of something going on, the unlikely is bound to occur. Before this isotope, the beryllium decays, if another helium fuses with it, it will form carbon-12, which just so happens to be stable. What I just described with helium burning is a triple alpha process, the main way carbon is formed. This is just a tiny part of the full alpha process, which we'll get to later. Another process called the CNO cycle is one of the ways that hydrogen is fused into helium. There are many CNO cycles, and there are similarities between them all. They almost always contain carbon, nitrogen, and oxygen. The starting nuclei is the same as the ending nuclei, and they all release helium-4 some point in the process. They may also contain fluorine, and even contain fluorine-19, which is the only stable isotope of fluorine. Let me give you an example. Carbon-12 and hydrogen fuse into nitrogen-13, which decays into carbon-13. Carbon-13 fuses with hydrogen to make nitrogen-14, which fuses with hydrogen again to make oxygen-15, which decays into nitrogen-15, and which fusing a final hydrogen atom will get us back to carbon-12 with an additional helium-4 atom. The CNO cycle is one of the main ways for nitrogen and fluorine to form. After helium burning, the core starts fusing carbon. Helium and hydrogen burning gets pushed out. So, what's carbon plus carbon? Actually, it could be many things. It could be neon-20 and helium-4, or it could be sodium-23 and hydrogen. It could be magnesium-24, or it could be oxygen-16 and 2 helium-4s. Although neon is heavier than oxygen, neon burning occurs first. Hydrogen, helium, and carbon burning gets pushed out to their respective shells, while neon is burning in the core. So what's neon plus neon? oxygen 16 and magnesium 24. Now, it's time for oxygen burning. All the other element burning gets pushed out, while oxygen burning is in the core. So, what's oxygen plus oxygen? It could be silicon plus helium, or phosphorus and hydrogen, or sulfur, or more magnesium and 2 helium atoms. Next is silicon burning, which is part of the alpha process. But what is the alpha process anyway? The alpha process, not to be mistaken as the alpha process, is when you keep adding helium-4 to your new elements. Carbon-12 plus helium-4 equals oxygen 16. Oxygen 16 plus helium-4 equals neon 20, plus helium-4 equals magnesium 24, then silicon 28, and so on. The part of the alpha process after silicon 28 is dubbed silicon burning. As usual, all the other shells are pushed out as silicon and helium get to work. Silicon 28 to sulfur 32 to argon 36 to calcium 40 to titanium 44 to chromium 48 to iron 52, and rarely to nickel 56. Now we have a core of iron, and you would think that our star would fuse the iron, but no. Iron needs more energy to fuse than it releases, and it just so happens to be the most stable element? That means that if protons don't decay, then everything will become iron at the end of this universe. Just thought that would be fun to share. With iron's refusal to fuse, there's no longer nuclear fusion in the star. Remember the equilibrium between gravity and the energy from nuclear fusion? Throw that out the window, or in other words, defenestrate it. Gravity is winning. The star compresses more and more until, wait a second, the electrons of the iron core are so close to the nucleus that they fuse with the protons to make neutrons. A positive charge plus a negative charge is no charge. This collapse of the core of neutrons is so powerful that it blows the rest of the star away. Actually, that's an understatement. The collapse blasts it away, causing a type 2 supernova. Supernovae are important for our research for a couple of reasons. Number 1, supernovae nucleosynthesis, which is basically nuclear fusion, but all at once during the supernova. This is one of the ways chlorine is formed. Number 2, cosmic rays. Supernovae are so powerful that sometimes they can accelerate particles to the speed of light. Technically, no matter can reach the speed of light, but you can get close enough. These are called cosmic rays, and if they hit heavier nuclei, the nuclei may break down into smaller elements. This is called cosmic ray spallation. This is the only way that lithium, beryllium, and boron are formed. Number 3, this is one of the places where the R process occurs. Huh? What is the R process? I literally just read your mind right there. The R process is responsible for over half of the elements heavier than iron. How though? The R process stands for rapid neutron capture, but what does that do? If I were to remember correctly, you get a new element for adding protons, not neutrons. Well, there's something called beta decay, which is basically a neutron turning into a proton and releasing an electron and neutrino. If you keep adding neutrons to the seed nuclei before other neutrons can beta decay, they can all decay at once to create some really heavy elements, like gold and uranium. The R process is the main way that many elements are formed. All the elements formed by the R process include, get ready for this, scandium, gallium, germanium, arsenic, selenium, bromine, krypton, rubidium, strontium, yttrium, zirconium, niobium, molybdenum, ruthidium, rhodium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon, cesium, barium, lanthanum, cerium, praseodymium, neodymium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, tholium, ytterbium, lutetium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, thallium, lead, bismuth, thorium, uranium, neptunium, and plutonium. Oh my gosh, that was a mouthful. Well, that was the R process. Oh wait, why does the R process occur? Yes, it occurs during supernovae because the core is literally composed of primarily neutrons, but where else? There are 2 other places where the R process occurs, Kilonovae and the hypothetical accretion-induced collapse of a white dwarf. First up, what is a kilonova? Remember that supernova that I talked about? When the neutron core collapses, everything else gets blown away, but the core still remains. The core of the dead star is called a neutron star because it's made of neutrons, and is one of the most chaotic things in this universe. If the neutron star is too big, gravity compresses it further into a black hole. If one is spinning, that's called a pulsar. And look at this thing. It's legitimately insane. Oh, and I guess it has a strong magnetic field. Wait, what's that called again? Magnetars? That is actually the coolest name that I have ever heard. Oh wait, I'm kind of off track, aren't I? Anyway, two neutron stars may orbit each other in a binary system, which is two stars orbiting each other. As they get closer and closer, they orbit faster and faster, until they orbit almost thousands of times a second, until they merge, of course. That was just one of the most violent things in the entire universe, a kilonova. During this collision, you could probably tell that there are a lot of neutrons to our disposal. This is where the really heavy elements form, like uranium and such. The neutron stars may merge to a larger one, or a black hole. The other place is accretion-induced collapse of a white dwarf. This is completely hypothetical, however there's been lots of indirect evidence. Accretion-induced collapse, which I will now refer to as AIC, occurs when a white dwarf is in a binary system orbiting another star. But first, we must explain what a white dwarf is. When a smaller star, like our sun, starts fusing helium, they can't really produce any elements greater in mass than oxygen. So when they run out of fusible material, they become unstable and blow away their outer layers, causing a planetary nebula, which are truly beautiful to observe, with a white dwarf as its dead core. Now, back to the binary system. The white dwarf, being super dense, starts eating the other star by taking material from it and accreting it. The A in AIC. The material may ignite on the surface of the white dwarf, causing a type 1A supernova, or a classical nova. Something fun about this is that this process repeats over and over again. The white dwarf gains mass and becomes denser until it takes too much. The greedy white dwarf becomes so massive that gravity wins. Like core collapse of a red giant, gravity is pushing so hard that the electrons get too close and fuse with the protons to make neutrons. Once again, there's a huge explosion, and the dead core's dead core is a neutron star. There are lots of neutrons to be captured rapidly for the R process. That was the R process and everything I know about it. However, we still have a handful of elements remaining. So, let me introduce you to the R process's brother, the S process. The S process is just like the R process, but slow. It stands for slow neutron capture. So instead of cheating beta decay and adding more neutrons, the S process decays when necessary and doesn't when not. It is a source for the elements lighter than iron, but aren't part of any burning process. I will only cover the elements the S process produces that we haven't gone over yet. So, the S process makes potassium, vanadium, manganese, cobalt, copper, zinc, polonium, and many more. Wow, we've covered almost all the elements, except for this cluster. It's elements 95 to 118. Oh wait, those are the synthetic elements. A synthetic element is an element only made by people and never found in nature. All elements with an atomic number greater than 95 are synthetic. But how do people make new elements? Well, we imitate the R process. We throw a bunch of protons, neutrons, and alpha particles, which is just helium-4, at nuclei with an atomic number less than 95, like plutonium, and hope that we get new elements. This has worked so far, and we've gotten an element with an atomic number of 118 called organosun. Synthetic elements include americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium, rutherfordium, dubnium, seaborgium, bohrium, hassium, meissnerium, damstatium, roentgentium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and organosun. Wow, who named these? I should have given them names that were easier to pronounce. We are almost done. We just have to go over the Outcast, starting with the daughter isotopes of uranium. A daughter isotope is a decay product, what an element decays into, of an atom. Uranium decays into many elements, including actinium, astatine, radon, francium, radium, and protractinium. No, that's not what protractors are made of. It's the Greek prefix protos, means first, which they added to actinium, because actinium is produced from radioactive decay of protractinium, so it means first actinium. I just thought that was a little fun fact. Almost done. Technetium is not a synthetic element, however, people make it quite often. It is formed naturally through spontaneous fission, a type of radioactive decay when an element splits into two, from uranium and thorium. But people make technetium by turning molybdenum-98 into molybdenum-99, which decays into technetium-99, which has a half-life of 210,000 years. So close. Promethium is formed through rare alpha decays of europium and spontaneous fission of uranium and thorium. It's synthetically made by bombarding neodymium and praseodymium with protons, neutrons, and alpha particles. And finally, aluminum is formed as a decay product when magnesium-26 captures a proton or neutron. Okay. Finally, we did it! We've covered every element and coincidentally the history of the universe as well. We learned about stars, supernovae, cosmic rays, beryllium-9. Carl and Mateo get this joke. Neutron stars, R process, CNO cycle, S process, core collapse, red giants, nuclear fusion, synthetic elements, white dwarfs, accretion-induced collapse, atoms, the Big Bang. To today, with me and you living on a rock, orbiting a star that is bound to form some pretty cool elements in 5 billion years.